In this problem, we have a branch office of Banco Mexicali. They observed during peak hours that an average of 30 customers arrive per hour. And there is an average of 3 customers in the branch office at any time. Notice here that the question does not say there are 3 customers waiting to be served in the queue or in the waiting line at any one time. There are 3 total in the branch. So this is 3 customers total in the system, not just in the queue. How long does the average customer spend waiting in line being served? Okay, so this is what we call a Little's Law question. So if we go to our slides, we can see Little's Law covered in the beginning of the lecture. And so where we have arrival rate is lambda, and L is the number of people in the system, and W is the average waiting time for a customer. Okay. So how do we know it's a Little's Law question? We're not given any information about the service rate. What is the service rate? We're simply given 2 parameters of the system, of the overall system, not queue separately from service. Queues and services all combined. For the overall system, we're given 2 parameters. We have to find a third. So that's how we know it's a Little's Law question. So L is 3. Lambda is 30 per hour. Okay, and W is what we have to find. L equals lambda W, so W is going to equal L divided by lambda, and that will be in hours. So the average time a customer spend waiting in line and being served. Again, this is another hint. This is a Little's Law question because notice you have to find the time spent not just in line and not just being served separately, but the total in line and being served. That is W in Little's Law. And so we know it's and there's no information about a server, how long the server takes, what is the service rate or the service time. And so we know we have to use Little's Law. So W is 0.1 hours. Okay. And the answer does want the answer in hours to 2 decimal places. So let's make sure. Yep, it is 0.10. Okay. Now let's do the next question as well. This question is about Solomon, Smith and Sampson law firm. Okay. Here we have legal documents that must be word processed for clients. The arrival rate of these documents or requests is 18 pages of documents per hour. So lambda, the arrival rate is 18 pages per hour. And they arrive according to a Poisson distribution. Secretary can process 19 pages per hour. So the service rate mu is 19 pages per hour. Okay. Average utilization of the secretary. So we have one server, which is the secretary, okay, and we have to find their utilization rate. Now, this is going to be an MM1 system. Why? Because the arrivals are Poisson and the service happens according to the exponential distribution. So these 2 things, Poisson distribution for arrivals, service times having an exponential distribution means it's MM, and there's only one secretary, so it's an MM1 system. Okay, so we can go to the slides, the slide which has the formulas for an MM1 system right here, and we can see that the average utilization of the system, rho, is given by lambda over mu. Okay, so if we do lambda divided by mu, okay, we get our utilization to be 0.947. Let's see if the question wants it in percentage. It does. And to the nearest whole number. So you have to multiply it by 100 to get on the percentage scale from a probability scale, because probabilities go from 0 to 1. And probabilities going to percentage, they go from 0 to 100%. And so to the nearest whole number will be 95%. Now the probability that more than 4 pages are waiting to be processed. So we need to find probability that n is more than 4. Okay, n in the queue, how many people in the queue? So the queue, right, more waiting to be, waiting or being processed. So it's a number of people in the system, that the number of people in the system is more than 4. Okay, this is going to be 1 minus the probability, you know, that you have 0 up to 3 documents in the system. Okay, right? So if you find the probability between 0 and 3 documents in the system, you do 1 minus that, you'll get the probability of 4. Actually, we have to do less than or equal to 4, because if you do 1 minus 0 to 3, that'll be 4 or more. But we have to find only more than 4, not 4 or more. That more than 4. So 4 is not included in the probability you have to find. So it's 5, 6, 7 like that. So more than 4 is 1 minus probability 0 to 4. Okay. Now, if we go back to our slide, probability of n units in the system is given to us by the utilization raised to power n and 1 minus times 1 minus the utilization. So we can make a table n 0, 1, 2, 3, 4, and we can find the p of n. That is going to be, we take the utilization, okay, and we raise it to the power n. That's the row raised to power n, multiplied by 1 minus the utilization. Okay, and I'm putting $sign, so when I drag the formula down, the utilization cell remains locked and the red cell moves down to pick the right value of n. Okay, so the probability that there are between 0 and 4 documents in the system will be the sum of all these individual Pn probabilities. That's 0.23688. We need 1 minus that, so probability that n is more than 4 pages are in the system is 1 minus probability 0 to 4. That'll be 0.763 is our answer, and we put it in. So notice there's no percentage signs. I got to put in as a probability and to 3 decimal places. So that will be 0.763. Okay. The average number of pages waiting to be processed. Okay, notice it says waiting to be processed, not being processed and waiting to be processed. If it was both waiting to be processed, that's the queue or the line, and being processed, and it'll be the total pages in the system. We don't need the total pages in the system. We only need the average length of the queue or the waiting line, because that's the pages that are waiting to be processed. So if you look at the formula, the average number of units in the waiting line, LQ, is given by lambda squared divided by mu times mu minus lambda. Okay, so we can do this right here. LQ is going to equal to, a top part is going to be lambda squared. Okay, so we take our lambda and we square it, and then we have to divide that by mu times mu minus lambda. So we're going to take mu, okay, times mu minus lambda, okay, and that becomes 17.05, and you run into 2 decimal places. So we have 17.05 pages waiting. And that was it for this question. So in this video, we solved 3 problems, a problem using Little's, a problem using Little's law, actually 2 problems, and then a problem using the MM1 queue. And this was the Solomon, Smith, and Sampson law from problem.